Swayam Prabha. Digital India. Educated India.
Portion of this course. Of course, we could cover a whole lot more, but I think this is sufficient in terms of the requirements of this specific course. So what I'll be doing, as I said in the last week, I'll be doing a couple of inverse problems using the techniques that we have discussed. Today, I'll be using physics-informed neural networks. I'll be using PINN for today's class. I had initially planned to use the direct surrogate model for today's class, but I have planned for a problem, but it turns out I've not done that specific problem in the course this time. So I'm just getting the data for that. So basically, I want to repeat with neural networks what you had done using conventional techniques, and I'll do that tomorrow. All right, so I'll just very quickly give you a recap of what we discussed about pins last week, and then we will actually solve the problem that I had sent to you. So remember, if we use surrogate models and you're trying to solve any problem, this requires very heavy data. This will become very clear once we do today's problem and tomorrow's problem. Okay. Further, surrogate models do not use the knowledge of our governing differential equations. In PINs, we can actually use information about the differential equations, and I need to point this out. Without knowing the solutions. Okay. So in many cases, for example, in the Navier-Stokes case, you will know the governing differential equation, but you don't know the solution to the differential equation. So in such cases, pins become useful, and you can incorporate experimental data as well, as I will show you in the example today. And these can be used for both forward and inverse problems. I'll be giving you only an example of an inverse problem, because in many ways, hidden within that is the forward problem also. Sorry, was there a question? Okay. If you have a question, please feel free to pause me. Okay, so suppose we are solving for the forward problem and know the differential equation. So I am just giving you a recap of what we already did. The key idea of the PIN is that the solution is a function, of course, and you can assume some functional form and leave some free parameters, which I'll show you today also. But this functional form could essentially be a neural network, and the free parameters could be the weight of that neural network. Okay, and what we do is we sample the equation at some points. As I told you in the last class, you could sample the equation if you know the temperature only at 4 points, but if you know that the differential equation is solved everywhere, you can sample everywhere for the equation and boundary conditions or temperature points at just those specific points. Okay. So one example which I'll be using again today in the exercise problem is to use a polynomial. So let's say you use a quadratic polynomial. You can impose this at certain points. If you have more points, as we saw in the last week, you can take a least square sense of this whole thing, and you find out what satisfies d square theta minus m square theta, d square theta dx square minus m square theta equal to 0. And you include some boundary points also in order to make sure that you are not getting a totally meaningless solution. Okay. You can use the neural network as well. So the neural network we could use is something like this: input one variable x, output is theta, and put some neurons in the hidden layer, let's say 10. The rest of it is exactly the same as the polynomial example, and you solve for w. Once you solve for w, you have theta of x. So that's the forward problem. You actually solve for the forward problem. The way you find out d theta dx and d square theta dx square is either you can differentiate this expression by hand, okay, which you can kind of do for simple networks, and possibly in an example in class or in an exam, I can give a simple enough network that you don't need to use something like backprop. But in other cases, you can use the backpropagation algorithm, or what is known as autograd or automatic differentiation, in order to find out d theta dx or d square theta dx square. And in order to solve for the weights, we can use gradient descent in case it's a nonlinear problem. Now, this is just for the forward problem. If I have some data in the middle, very similar to the example that I will be doing today, you can use the same method remarkably enough to solve for inverse problems also. This is the distinction between a pin-based inverse problem versus something like what you have been doing throughout in this course. And once again, like I said, I'll make it clear once I show you the example now. If you have the data and the differential equation, where do you have at as many points as you want? Data you have at some limited points. Here, let's say using thermocouples, you measured at 4 points. But we do know that every point, even when I don't have the thermocouple measurement, my differential equation is solved. So that's the real idea behind using pins there. Now we treat this m also as an additional unknown weight to be solved. So you approximate theta of xm and you have multiple weights. You don't need to solve it only in this way. There are multiple other ways of doing it, but this is one way of doing it. Okay, you solve for optimal w and optimal m, and the optimal m is the inverse problem solution. So just like I told you before, you have ODE error and you have theta measured at these 4 points, the error for that, and you optimize so that this error is minimized. Okay. So typically it will require far fewer points than the surrogate model, and really speaking, you don't need to get some extra data from somewhere else, and this can work very well, and it's very competitive with traditional techniques. Okay, and in many cases it can actually be faster. Okay, so I'm going to show you a example problem now, and we will try and solve it, slowly as we do it usually. So we did several problems. I have just listed 2 because I called it problem 3. So I just wanted to remind you of the problems we have looked at so far. We did forward pass for a neural network. We also did sort of a little bit of the reverse pass, but not by much. We of course did gradient descent in some detail for linear regression in a slab last time. And here is the problem. Imagine that there is a slab, one-dimensional wall. Let's say this is x is minus L, x is plus L. This x is 0 at the center. And 2L is 50 mm, so basically L is 25 mm. And what I know is that there is uniform heat generation. Okay, so there is uniform heat generation. Uniform means QV is a constant throughout the domain. So there is heat generation within the wall. Okay, and we know that the thermal conductivity is 50 watt per meter Kelvin. So K for the wall material is 50. And we measure temperatures at some 7 locations that I have given here. Okay. I have kept them at uniform locations. So let's say we have taken these 7 measurements. Temperature measurement in degrees centigrade is given here. Okay. If you look at it, you will see roughly that it first increases and then it decreases. So it's somewhat like this. But you will see the data is somewhat noisy. I added some noise to this data deliberately. Okay. So we have some temperatures here. So the question is this: using a physics-informed neural network approach, okay, we need to find out what is QV. Okay, so you understand the inverse heat transfer problem now. I have given you the temperatures and I want you to find out QV. So typically this is actually from the heat transfer. The problem I have taken is sort of the corresponding inverse problem to the problem which is there in the textbook by Professor Balaji, myself and Dr. Satish Gedupudi on heat transfer. All of you would have done the forward problem in class, which is I give you a temperature, I give you QV, then find out what what the heat flux is, etc., etc. Here we are asking you to find out what is QV given some temperature measurements. Okay, some discrete temperature measurements at some 7 locations. Okay, also find out heat flux at the 2 walls. Now, technically speaking, when I give some such problem in a physics informed, of course, it's called neural network. What I should do is I should assume that the temperature is an output of a neural network. Okay, so let's say there's a bias unit here. And let's say some 3 neurons, and output is temperature. This should generally be the approach that we should take. But for ease of hand calculation, we are going to assume that the temperature is a quadratic profile. This works well, of course, because the temperature indeed is a quadratic profile when you have a uniform heat generation. So we are going to assume that temperature looks like W0 plus W1x plus W2x square. So this is what we are going to assume. And the question is find out QV. Given that T is of the form W0 plus W1x plus W2x square, also find out the heat fluxes at the 2 walls here and here. Okay. What is the Q? You are given temperature measurement. Okay. So K is 50. These 7 temperatures are given. Let me just show this data here. Find out QV as well as the heat fluxes at the wall. So use PINN to do this. So this is the basic question. So how do we set this problem up? So please think about this for a minute and let me know how you think we should proceed. So any ideas, suggestions, please go ahead and tell.
We assume some value of QV first. Since the differential equation is known, we can try to, in this case, the differential equation is simple, so we can try to solve it and obtain a analytical solution for T by assuming a value of QV. Then we try to find the values of temperature at different locations and we find the errors.
Okay. So what you are saying is not an incorrect approach, but that is basically not the PINN approach. Okay. So you are assuming that you can solve for the differential equation. Okay. But we are going to proceed blindly, assuming we cannot solve for the differential equation at all. That is the power of the PINN approach. So suppose what is the differential equation incidentally? Without that, you can't do PINN. You have to know the governing equation. So what is the governing equation in this problem? Does somebody know?
d2t dx2 plus qv by k is equal to 0.
Okay, very good. So d square t dx square plus qv by k equal to 0. Okay. So this is the governing equation. So now using a PINN sort of thinking procedure, I see this as one type of data. I will call this ODE data. What do I mean by data? I know that this governing equation is satisfied at every point here. I can take as many points as I want. I can say, if I can impose this somehow without solving for t, okay? If I can impose it directly in the governing equation form, I can impose it at 10, 20, 30, 40, 50, how many ever points I want. Apart from that, this is actual temperature data which I measured on the ground. This is temperature data. Okay, so two different types of data, ODE data, temperature data. And I want to incorporate both these in a machine learning framework or in an optimization framework and try to find out what is the appropriate QV. Okay, so just for convenience, let's call QV by K as Q. Okay. This is not really correct notation. You can call it Q prime. I will just call it Q because it's easier for me to write Q instead of keep on writing Q prime everywhere. Okay, so I'm just defining Q as QV by K. So once we solve for Q, of course, we can multiply by K and we will get QV also. All right. Okay. So here is how we do PIN. Somebody else suggestions how we can do this? How can I incorporate both this as well as this data?
So
Use the equation in cost function.
How do we create the cost function? So I have to create one total cost function. This cost function is going to be cost function due to the ODE plus cost function due to the temperatures. Correct? So how do I write the cost function due to the ODE? First, I have to select points where I will impose the ODE. So which points can they be? For now, I will select the same as the measurement points. These are the 7 points. In general, you can choose as many as you want, but I am choosing to take the same 7 points where I have measured. I am going to impose my ODE just there. Is this okay? Okay, you will see a few things emerge from here once we do this. Okay, so we will select the same as the measurement points. Okay, so what is JODE? Let us say I come to a point. Let's say I come to xi. JODE says d square t dx square at x equal to xi plus qv by k. This also should be at x equal to xi minus 0 square. Does everybody agree? Is there any question about this? Please do ask me. This is a key step. Please do ask me if something is unclear. All I am doing is d square t dx square plus qv by k should be 0 here. In general, because of the choices we have made, they will not be 0. So I am going to find out the difference between what d square by dt x square plus qv by k is and 0. So this minus what it is supposed to be square. This is what my data gives. This is what it should be. Okay. So this minus this square. Okay. Everybody fine with this? Okay. Now if we look at it, What is d square t dx square? I have chosen t equal to w0 plus w1x plus w2x square. So this will give me, what will it give me here?
Twice W2.
Twice w2. Okay. Plus qv by k is q. Let us call this w3 because it's one more unknown in my problem. I don't know what qv is, so I am going to call it w3 plus w3 square. Is this okay? So this is my J due to the ODE. What is J due to the temperature? Can somebody tell me?
Ti minus the T hat whole square.
Temperature at that point minus predicted temperature, the whole square. This is the actual experimental value. This is my predicted value. Okay. So I am just going to flip the order because it's easier that way. I am going to write Ti hat first. So this is going to be W0 plus W1 xi plus W2 xi square minus the experimental temperature measurement, these values here, squared. Okay. So these two have to be summed up. So I am going to write J equal to, this is the same for all of the endpoints. Okay, I have endpoints 1, 2, 3, 4, 5, 6, 7. So this is going to be summation of 2W2 plus W3 square I equal to 1 to n. This is, it turns out to be a constant. It doesn't seem to depend on n, plus W0 plus W1 xi plus W2 xi square minus Ti experimental. I'm just going to call it Ti square I equal to 1 to the number of points. Number of points here is 7. Okay, so now we have the cost function. So our problem is simple. Find W0, W1, W2, W3 such that J is minimized. What happens if I do that? As part of the solution, I get W3 also, which happens to be the QV that I want to determine. Okay. This is part of the solution. Okay. W3 is QV by K, so I can find out what QV is. Is this clear? All right. So how do we proceed from here? Once that we have I have found out a J to minimize. So how do I move ahead?
We assume some values of W0, W1, W2, and W3, and then with gradient descent.
With gradient descent. That's one approach. Okay. So whatever approach we take, so we need to find turns out there are two ways for this specific problem. Typically, you will have to direct approach was that there is the direct approach, and then there is using gradient descent. Okay. What is the direct approach? Direct approach is we directly solve for grad j with w is equal to 0. That is del j del w0 is 0, del j del w1 is 0, etc. etc. Gradient descent, all of you have seen, both in the exam as well as in the class. So in either case, I have to calculate grad j. So let us first do that. So can somebody tell me what del j del w0 is? Can somebody tell me this? Del j del w0? You can look at the equation here. If you wish, we can write this again. This is almost identical to what we did earlier. So this should not be difficult, hopefully. Del j del w0?
2 into summation of.
I'll call this y hat to be consistent to our usual. Actually, let's put a half everywhere. Doesn't change the problem. It makes the differentiation a little bit easy, and also for gradient descent, it's a little bit easy. Okay. So sorry, go ahead and tell me del j del w0 is?
Sir,
Summation of the second term, W0 plus W1 xi.
Yeah, so another way of putting it is, we had done this before. Ujjal, you were going to say something?
yes, sir, I was going to say the same thing.
Yeah, so this is y hat I minus yi. Correct? Especially if I put the half. So square cancels. You simply get w0 plus w1 xi plus w2 xi square minus ti, which is y hat I minus yi. This becomes, by the same logic, this becomes, what should you get for del j del w1?
Into
xi.
Say into xi. Good. This
xi square.
But there is an additional term.
Yes.
So what do we get?
2w.
N into 2w2 plus w3.
W3. Is that it, or do we get another factor somewhere?
We get another 2.
another
into
2, sir.
Another 2. Okay. And the final equation?
N into 2w2 plus w3.
N into 2w2 plus w3. Okay. So when we do a direct approach, luckily you will notice all these are linear in w2, w3, w0, w1. So either you can solve this is equal to 0, all these 4 equations equal to 0, and you will get a solution for w0, w1, w2, w3. Direct approach would be that. Okay. Solve for, so direct approach. W0, W1, W2, W3 with grad j equal to 0. Okay. So these are 4 equations in 4 variables. This will be a linear system of equations, just like we did for linear regression with 2 equations and 2 variables. You can solve this. There are a few tricks you can use. It turns out to be fairly easy. But I will not do that. Okay. I want to show you a few things with the gradient descent because that's what is general. Why? Because in this case, we took a quadratic equation. If you take quadratic, cubic, any polynomial, you will end up with a linear system of equations for this specific problem. Okay. In fact, even if you use the fin problem, it will not turn out to be linear because you have m square. Okay, you have the fin parameter, and that will make the problem non-linear. You will no longer be able to solve it like this. Okay. So we can use gradient descent. And in gradient descent, what do? I have already calculated this. So Wi equal to Wi minus alpha del J del Wi. Notice when I do that, I am updating both the weights which are sitting in the temperature as well as W3, which was my volumetric heat transfer. So notice this, that is also getting updated during gradient descent, the parameter which we don't know. So suppose you do the the fin problem, your parameter M will also get updated along with the weights. So this is the sort of, I find it's a really neat method. Okay, so you solve for every parameter along with the inverse problem that you're solving for. You solve it all of them simultaneously using gradient descent. You update, okay, and you end up at the solution. Now, when we use gradient descent, I gave you sort of something similar in the exam also. Remember that it is always best to normalize, otherwise it becomes a very difficult problem to normalize with respect to at least the independent parameter. Okay, in practice, okay, in theory you can do without that normalization. Well, even in theory you have to be careful. Normalize the independent parameter, that is x. When I say normalize, what I mean is instead of it going from minus 25 to 25, I will say that it goes from 0 to 1. Okay. So let's call this x prime. Okay, remember x goes from minus 0.025 to plus 0.025, whereas x prime will go from 0 to 1. Okay, so this point now in x prime coordinates will be x prime is 0, and in this point will be 1, and we can basically, since these are uniformly distributed, we will just linearly shift everything. So this will probably be 0.142 or something. I think this is 1.36. Okay, 6 points. So 0.166, 0.33, etc. So this point will be exactly 0.5 in the middle. Okay. So x prime will go from 0 to 1. X will go from minus 0.025 to plus 0.025. So I wrote a code for this. Okay. Can everybody see my MATLAB screen?
Yes, sir.
Yeah. So what I have done, I mean, I wrote a general code, but what I have done here is 7 points. I have now initially written x as we had in our data file from minus 0.025 plus 0.025. The temperatures that we have measured are here. Okay, I have written them as I had written in the data file that you saw, and I have also normalized x. You can see this. Okay, I have done this normalization so that now it goes from 0 to 1. You can now see my initial values of W. I have taken the a very simple initial value. There are questions even in neural networks about how to initialize these. You should not take them to be 0, 0, 0, 0. You should do all that. But in this problem, it works. So I'm not going to bother with it. So I have just taken 0, 0, 0, 0. Learning rate I have taken to be 0.01. Through trial and error, I found out that this kind of works. 30,000 epochs means I will go through 30,000 iterations. How did I choose 30,000? Again, by trial and error, I did that. You can now see y hat. Now, please remember, this will be a little bit confusing. All my W coefficients are offset by 1. Okay. So my W0 on the theory calculation is now W1. So now I am calling it W1 plus W2x plus W3x square, and then W4 will be my QV, okay, volumetric heat transfer. So error is what I am calling that y hat minus y because it keeps on occurring. So you can see that my first gradient is y hat minus y, second gradient is y hat minus y multiplied by x, third is y hat minus y multiplied by x square plus there should be a factor of 2 here. And fourth is, okay, so I think I have a minus sign which is off. It doesn't matter because it will just give you the negative of the value. Let's check if it works. Okay. So all I have done is W is W minus alpha times del J del W. Okay. I'm just printing it out. And I'm going to finally print out what it looks like. Okay. So let's see how it works. Yeah, so here you can see, I hope you can everybody see the figure?
No, sir.
No, you can't. Okay, let me just see if I can. Now?
Yes, sir.
Yes, sir.
Okay. So now you can see that after so many iterations, these were our original points. Okay. They looked far more confusing on the data table itself, but on the plot, you can at least see this quadratic trend very clearly. The red points are our experimental data points, and now it has fit a nice curve in the middle. The quadratic curve. The quadratic is what we guessed, but we guessed it and we made it satisfy the differential equations at these points in a least square sense. Okay. And we also made it satisfy that it has to fit these points somewhat reasonably for a Q which we don't know. Okay, so that's the remarkable point. The point is, we said d square t dx square plus Q equal to 0. There I don't know the Q at all. So, but it is finding out the optimal Q which will both fit a curve of that shape as well as these points. Okay. So once I do that, let us see what values of W we get. Okay. So please write these values down. I'll also try and write these down here. So 198.7624. Okay. That's our 198.7624, 4.8246 minus 4.8178 and 9.6355. Okay. Let me see if I can copy paste it. Okay. So these are the values that we get. Oops. Are all of you able to see my screen?
Yes, sir.
Good. All right. Values that we got. So this one is, I'm going to call it W0 prime. Why am I calling it prime? Because this corresponds to X prime. This doesn't correspond to X. Okay, so here are the questions. What is QV? What are the fluxes? on the walls. Okay, so how do we approach the first question? How do we answer this? Thoughts?
For W3, we first convert it into the actual coordinates and then multiply it with Q.
Okay, so you are saying, sorry, just tell me, W3.
Yeah, we need to first convert W3 prime into W3 means an actual coordinate.
Right. So we need to convert W3 prime to W3. So how do we do that? How do we convert? For that matter, how do we convert W0 prime to W0, W1 prime to W1, W2 prime to W2? Thoughts? Okay, what I will do is, if you have any questions, you can ask me. I have a couple of minutes left, but I will stop here. I will discuss this since we are actually done with the theoretical portion. I will discuss this tomorrow along with the other problem, but I would still like to hear your thoughts on this. It will take me about 5 minutes to finish this up. Unfortunately, that call kind of interrupted. But yeah, so any thoughts? How do I convert W0 prime to W0, W1 prime to W1? W2 prime to W2, and as was rightly pointed out, if I convert W3 prime to W3, then I can multiply it by K and I will get my QV. That is perfect. Of course, for finding out heat transfer at the wall, I will also need W0, W1, W2. So I need from W0 prime, I need to go back to W0, and W1 prime, I need to go back to W1, etc. So any preliminary thoughts, or if you have any questions or doubts on what I did so far, please do feel free to ask.
So like in the loss function, if we have W1 into X, so the factor by which we will scale X, we will scale down W1. So the product should remain constant.
The product should remain constant. It's the intuition is almost correct, but it's not absolutely correct. Okay. Your idea is almost correct. Okay. And it would be perfectly correct. Let me even point out if there was no shift in origin. See, if I had made this, if I made it 1,000 times, just to give you, or if it goes from -1 to 1, then your intuition is correct. Okay, so then X prime and X are just scaling, but there is an offset, na? So because of that, it won't be perfect. It will not exactly scale. It will not do that. So by what you are saying, the scaling W0, W1 X prime, W1 prime X prime is the same as W1 X, correct? That's what you are saying. Yes. And W2 prime X prime square is the same as W2 X square.
Yes, right? Sir.
Yeah, and W0 prime would be the same as W0 in that case by the same logic, correct?
Yes, sir.
What would happen to W3 incidentally?
Sir, once we get W2, we can get W3. So the sum should remain constant.
Yeah, do think about this and we will meet tomorrow. Anybody else have some other thought?
Sir, writing the equations in terms of mu x.
So writing the means if we try to find the dimensions of the parameters, for example, in this case W3 prime, we can find the we can try to find the dimensions of this parameter, and for W3 we know the dimension will be equal to watt per meter cube divided by watt per meter Kelvin. Now in this case, we have normalized the value of x. So
Correct.
that means the length parameter will be completely eliminated in the W3 prime.
Hmm.
And on the right hand side, we have but we require means a parameter, the dimension of meter
Hmm.
in W3. So accordingly, we can
Yes, but that effectively comes to the same idea that was pointed out, which was W1 prime x prime should be the same dimension as W1 x1 x, correct? So now what is the factor which is sitting up front? Is there a factor? Are you adding 2-3 things? So just do think about this a little bit further and tell me how we can do a one-to-one map tomorrow in class. So we will start from here tomorrow, and I will also do the other surrogate model example, and we will end tomorrow. Okay. Thank you very much.